To answer why animal models are still important, I will use cancer research as an example, since it represents a large part of our work. Right now, there is a lot of interest in boosting the immune system to help fight cancer. For example, AI can help us identify the most effective molecules, and in vitro methods can help us confirm that these molecules are acting on the right targets. But how we know where in the body a candidate drug will actually go when it's taken as a pill or injected in the bloodstream? Thanks to an animal model. The systems we study are very complex, and current technologies are not yet enough to rely only on computers and cell cultures to understand all the mechanisms and how they interact. It will be like trying to understand how a whale lives by only observing the surface of the ocean. So we need to dive in. If we want to better treat cancer and many other diseases, we still need our mice. In silico, in vitro and in vivo approaches have always complemented one another. In fact, all of these methods are systematically used during drug development. As a reminder, every candidate drug must be tested in animals before entering clinical trials, that is, before being tested in humans. Therefore, NAMs and animal models already work together. This is even more evident in mice with a humanized immune system. These cutting-edge models create a stronger bridge between NAMs and humans than more traditional animal models. Using humanized mice increases the likelihood that a candidate drug will produce effects similar to those observed in humans. Just like NAMs, humanized models are at the forefront of current research. These approaches are complementary and must continue to evolve so that collectively we can pursue a more responsible use of animals. Perhaps one day, when a person develops cancer, doctors will be able to collect cells from both the patient's immune system and the tumor itself. These cells could then be grown and made to interact with one another using organ-on-a-chip systems. We can even imagine reprogramming these cells into stem cells and then differentiating them into dozens, hundreds, or even thousands of different cell types, recreating all of that person's organs. Dozens of drugs could then be tested to determine which ones are the most effective in that specific context. A few mice or another species, humanized using cells from the same patient, would then receive the most promising treatments to identify the one most likely to save that person's life. Once recovered, the patient could return home with the animals that directly helped guide their treatment. In this way, each would have given the other a second chance in life.